And let's sort of look at the constructors in a little bit more detail and see how we can actually simplify its definition. So this is one of the ways for defining a constructor. There's several different ways for doing that actually. So there's also another way for you to define a constructor. Let me just write it first before I explain it. And the input is still the same, but this time let's comment out this particular section of the code. Let's comment out this particular constructor. But this time I'm going to write it in a different way. I'm going to use a colon, and then I'm going to use a initializer list. So how do I use the initializer list? So this colon has a very special meaning. If later on when we talk about the class inheritance, you'll find that this kind of syntax has similarities with inheritance, but it's not inheritance here. The only thing that's going to happen is to do initialization. So name is going to be the private data name, data member, that's name. And then here I'm using the universal initialization. I'm actually using name, NAM, that's one of the input parameter, NAM, to initialize the name, that private data member. A name is a string. A string is an object. So a string object has its constructors, and this particular initialization is just going to initialize the name, the string name here, using the input parameter, that's the input string NAM. Right. And I'm going to initialize the age also. I'm going to initialize age with ag, the integer. The integer is not exactly an object, but it's still a container. But it's just a sort of a simple container. It stores an integer. One of the good things about C++ is that you can treat your own data types like a class, just like you treat those built-in types like an integer. And you can also do things the other way around. You can treat the built-in types like the integer, just like those self-defined, those user-defined classes. If a class or an object can accept an initialization, and then the integer, this kind of primary built-in data type can also accept a initialization list. So age is the integer. It can accept this kind of universal initialization. You can do that. You can initialize age using ag. And then the third is another string, that's sex. So you can initialize sex with se. And then the last one is a vector of floats. So you can initialize vitals using vi. So this initializer list, this list of initializations is not exactly in the body of the function. It's actually following the function declaration, function name and other informations with a colon. So it's not exactly in the body of the function. So in this way, you don't really have to define anything. You don't really have to sort of write any statements in the body of the constructor. You can just leave it empty. You can just leave it empty. There's nothing wrong with it. There's nothing wrong with it. And in fact, you don't really need to sort of put those initializations into the body of the constructor. And there's also benefits for doing that in terms of efficiency. And also in terms of other things, once we talk about the constants, if you have constant data members, that kind of thing, a constant data member can only be initialized using this kind of initialization list, following the colon behind the name of the functions. You can also initialize a constant inside of this body of a constructor, function body. Right. And it also has efficiency reasons. Doing the initialization like this is a lot more efficient than actually entering the body of the function and then executing those assignment those assignment statements, and the function is gonna the constructor is still gonna perform exactly the same as before. It's still gonna you're gonna still have exactly the same effect as just using this ordinary function, ordinary constructor function. So let's just save it, and then let's see if it passes the compiler. Yes, it has passed the compiler. And then let's run it and see if this p.print is still gonna print out the correct information. Yes, it's still printing out the correct information. Name Bob, gender male, age 30, and then a sequence of vitals. So this constructor is still works, just fine. We can further improve the efficiency of this constructor by making it an inline function. So if we have used the C language before, or previous versions of the C++ language before, you might have used the keyword inline, and which is the basic mechanism for making a function or any function a inline function. And what exactly is an inline function? Inline function is an idea to improve the efficiency by replacing function calls with the text of the function, the body of the function. So whenever the compiler actually sees the inline keyword, it's going to replace any call to this particular function with just the actual code, from this particular function. So this kind of strategy actually improves the efficiency by avoiding function calls, basically, because function calls are kind of expensive compared to other kinds of statements. A function call has more overheads than other kind of statements in a particular language. So it's always a good idea to avoid function calls. But the expense is that you are increasing the size of your source code now. So basically, you are actually just replacing function calls with the entire body of a function. So people usually inline functions that are quite short. And for this particular constructor, it is indeed a very short function because, for example, the body of the function is actually empty. There's nothing inside of the body of the function actually. So it is a good candidate for inlining. To inline this constructor, all we have to do is to actually move the function definition from outside of the class to inside of the class. So all we have to do is to move it into the class definition. So what we have to do is to just put the line here, and then comment out this old line. We don't need this declaration anymore because the definition is already there. But you have to remember to remove the scope, because the constructor function is already defined inside of this class. You don't really need this scope anymore. You don't really need to tell the compiler it's for person class. So you can just remove that, and then let's just save it and build it. Again, it should work. And it's gonna print out the correct information for Bob actually. So you can actually inline this particular constructor. At the beginning of the video, I talked about the default constructor. What I was telling you is that if you don't provide a constructor, by yourself, then the system is going to synthesize a default constructor for you. What exactly is a default constructor? A default constructor is a constructor that takes no input. So if you want to write a default constructor by yourself, you can do that just by defining a constructor that takes no input. So that's perfectly legitimate, and that's going to be, if you do not write your own default constructor, or if you do not write any constructor by yourself, then the system is going to synthesize this kind of constructor for you. But suppose I do not define this default constructor by myself, and I have just this particular constructor that takes a bunch of inputs, basically initializing every member of the private data members. So what's going to happen if I define an object P1, for example, without any initialization? Suppose I do a person P1, and then without any initialization, what's going to happen? Right, let me save it and build it. And it's actually telling me, it's actually giving me an error message. The reason is that once you have defined your own constructor, it doesn't really matter. It doesn't really matter if it is a default constructor or not, because for this particular constructor, it actually takes the input, so it's not a default constructor. Right? But as soon as you actually define your own constructor, the system is not going to synthesize a default constructor for you anymore. So if you really want to define an object without initializing it, and you have already defined your own constructor that takes inputs, you have to write your own default constructor also. So in this case, you have to sort of you have to define a function that takes no input. You have to define a constructor that takes no input. And again, we're gonna sort of do this initialization here and make the function inline. So I'm gonna initialize it just to initialize name to just an empty string, and then age to 0, and then sex to an empty string, and then vitals. I'm gonna initialize it to a vector of floats and with 3 zeros. And then the body of the function is going to be empty. So this way I have defined my own default constructor. And this time it should actually recognize this particular line, because I'm not actually providing an initialization information for P1, but it's going to call this particular constructor. It's going to call this default constructor for me. And this default constructor is going to do some initialization for me. So I made a mistake. So here it's not a square bracket; it's supposed to be a curly bracket. So that was actually the compiler was actually complaining about this mistake. And once I have corrected it, I can just rebuild it. So this time it passes the compiler. So you can also see that I have actually 2 constructors defined for this particular class. So the constructor can be non-unique. Both constructors are called person, right? The function name is the same, but the input is different. For this particular constructor, it takes a bunch of input, and this one takes no input. So C++ actually knows these are 2 different functions, and it's gonna choose the right function when you actually try to initialize, when you try to actually define objects. So here I'm actually define. So here, if I define a person P with a bunch of initializations that's inside of the universal initialization curly brackets, then it's going to call this constructor, because I have inputs, I have initialization information. And then when I define this person P1 object of person, I have no inputs, I have no initialization at all, so it's going to automatically call this default constructor with no input or no initialization, and it's gonna do the initialization with some dummy information. For example, name is gonna be empty, age is gonna be 0, that kind of thing. So this is another example of function overloading. So in fact, I'm actually overloading the constructor function of this particular person class here. And if I want to do a P1, if I want to do a P1.print, it's gonna print out the information that's stored in P1, and let's see what's gonna happen. So the information inside of the person P is gonna be Bob, male, 30, vitals, and then the information stored in person P1 is gonna be name empty, gender empty, age 0, and vital 0. So you can sort of see what's sort of the difference caused by different kind of constructors, And suppose I have incomplete information for initializing a person. For example, if I want to define a person, a P2, and then all I have is sort of the name of the person, So what I have to do is to just give it, for example, Bob, or give it a different name, Kevin, and then I have no other information about this person anymore. So how do we actually do we really need to write another constructor to take into account this kind of a situation, right? So let me save it and let's build it. And it's actually complaining. It's actually complaining it cannot find the correct constructors for this particular call to the constructor. So what are we gonna do? Are we gonna really write another constructor? Uh, Not necessarily. Not necessarily. We can actually sort of modify this particular constructor. We can modify this particular constructor. How do we actually make modifications to this constructor to take into account of this kind of a sort of situation, right? You can do that by giving default values to those input parameters. So suppose I sort of assign AG to 0, assign 0 to AG, I mean, and then assign SE to empty, and then assign the vector floats to another vector of floats, but initialized to 3 zeros. So now let's give it a try. Now it has passed, and it has passed the compiler. So that's sort of the set of. So basically you can give default values to any of the input parameter, and once you have defined those default values, if you have assigned those default values, if you are missing any of the inputs, for example, here I'm actually missing uh, the sex, the age, sex, and the vital information here. Then it's gonna use those default values that's already assigned to those input parameters. So that's one of the ways for saving some typing. For instead of defining a new sort of constructor, you can just use default values to avoid writing a new constructor that take into account just a initialization with just a name. If you sort of now if you do a p2.print, maybe I should modify the print function so that the printout looks easier to recognize. So I'm gonna print out a divider. I'm gonna print out a sequence of lines, and then that's at the beginning, and then I'm gonna print out another sequence of another divider. So here's one divider. I'm gonna do another divider, so it's gonna easier for me to let me build it again, and then I'm gonna run it. So you can sort of see this is sort of the value that's stored in P, in person P. That's Bob. Initialization is complete, so everything is in there, and then that's the sort of construct for that's for P1. So no initialization information at all, right? And then it's gonna print out a sort of empty 0 and O 0. And then that's for P2. Initialization with just the name Kevin. And then gender is empty, age is 0, and then everything else is 0. So you can sort of see how by using default constructors how it's gonna work. But one of the things about default constructor is that you can only assign default values to trailing parameters. So suppose you would like to assign an age, for example, here. You initialize with just an integer age, for example, age of 10, for example. Right? It's not going to work. It's just it cannot even assign the 10 to the string, to the name, and it won't actually pair the 10 with the age. It cannot do that. The C++ cannot actually automatically pair a initialization value for the middle of the parameter list. You can only replace values with default values for the trailing parameters, actually, for the trailing parameters. So if you have initialization for the name, it's gonna work. But if you have missed any initializations at the beginning, and you are just giving a default, for example, for the sex, or default for the, if you are assigning a value to age, or assigning a value to the gender, it's not going to work. Or you are assigning a value to the vector, it's not going to work. So suppose you assign a vector of floats, initializing in the initialization list, and this time it won't work, and it's actually telling you there's a error message here. So you can only assign default parameters. You can only assign default values to those trailing parameters instead of the uh, and if you actually do a person P3, for example, person P3, and this time I'm going to initialize not just the name, but also I'm going to initialize both the name and also the age, for example. And then I'm going to give it age that's like 20 or something. And then I do a P3 dot print. And let's see if it's going to pass the compiler. So this time it passes because I have assigned a name and then also an age. Even though I did not assign any initialization values for sex and vitals, but it actually knows that it actually knows to use the default values that's sort of given to it. Use those default values. So now let's build it. Building is fine. Let's run it. So this is actually for P3 for P3. So the name is right, but gender is like empty because I did not assign I did not actually initialize the gender. I only initialized the age, and the age is actually happens to be the second parameter inside of the input list. And then vitals age, so it has an age of 20. So initialization of age is fine. And then the vitals is all empty also. So the sex and our vitals are all empty. Of course, you can sort of initialize it using sort of one. You can assign values to sex and neglect the values assigned to vitals, right? And this time it's gonna pass. So now you have name, sex, and age, and then the vitals are still empty because you are using the default values for the vitals. You are using the default values for the vitals here. And of course, if you would really like to sort of just initialize, for example, the initialize only if you really want to have the capability to initialize only the age and, for example, the age and gender, then you will have to write another. You will have to write another constructor. So here you probably, if you want to account for this kind of situation, you really have to sort of write another constructor, person. So int age, and then string se, this kind of thing, and then you just initialize age to age, and then sex to se, and then leaves the body of the function empty. I probably have to sort of assign some default values to the vitals. So name can be sort of empty, and then vitals can be, just copy this thing over. So this time the vitals are like printing out all zeros because but the initialization order, it's actually giving me some kind of warning message because the initialization order is like different from the order that I was sort of using for defining the data members. So it's probably still better to actually move it over. I'm gonna move it over here. gonna be name, age, sex, and then vitals. So this time let's see if let me just run it. Name, age, sex. Okay, so that actually allows us to sort of account for lots of different kinds of situations in the constructor. Now let's look at the disruptors. The disruptors is supposed to handle the cleanup of the object. How it's gonna handle the how to destroy the object in a clean and in an efficient way. So how do we actually define a disruptor, right? So constructor has exactly the same name as the class itself. Then destructor actually also is related has some portion that's sort of similar to the class name, but except that you have to append the wiggle to it in front of the class name. So this actually gives you a destructor. So basically that's the name of the class with a wiggle or tilde in front of the class name, and then that gives you a destructor. A destructor usually don't really take any input parameters usually, so you can just um, uh, handle the cleanup inside of this function body. All the data members that we have defined for the person can handle its own destruction by itself. For example, this vector of floats. This vector class can handle its own destruction by itself. So it's an object, and the vector object has its own destructor. So we don't really have to write our own codes to clean up a vector. String is also a C++ standard object, a standard library object. So it also has its own destructor. So we don't really have to write our own codes to handle the destruction of the string object. The same is true for the string here. And then the age is just an integer. We don't really have to the integer knows how to destroy itself. So we don't really have to do anything. So we can just leave the body of the destructor empty. But what I would like to show you guys is to show when the destructor is called. So what I'm gonna do is that every time a destructor is called, I'm gonna display destroying. I'm gonna display this particular text and then name. The name is basically the name here. That's the name of the person. I'm just gonna do this kind of printout. I'm just gonna do a printout when the destructor is called. So here I have defined a person P, a person P1, and then a person P2, and then a person P3. So for the person P, it has a name of Bob, right? And then for person P1, it doesn't really have a name. For person P2, it has a name Kevin, and then P3 it doesn't have a name, but it has an age or something. So we're gonna maybe a good idea is to call maybe sort of I'll put an end of line here, and then I'm gonna call print. So basically I'm displaying a line, and then I'm gonna display the information. I'm gonna display the information of the object. So here's the output. Here's the output, screen output of the code. So that's when P was initialized, and this is when P1 was initialized, and then this is P2, and then this is P3. And then let's look at the ordering. Let's look at the ordering of the destructor. So this is when what? This is when P3 was destroyed. It's calling destroying. Basically, this information is basically P3. And then this is calling the destructor of P2, basically. That's Kevin. and then this is actually destroying the the person P1, and then the last one is sort of destroyed is Bob. That's the person P. So you can sort of see the order of destroying objects is actually the opposite of defining those objects. So I define the person P with the name Bob first, and define the person P3 with age 20 but has no name last. And then when the function ends, before it actually returns 0, these three objects are destroyed in a reversed order. So P3 was actually destroyed first, and then P followed by P2, and then followed by P1, and then followed by P. So when does the system actually call the destructor? It calls the destructor when a particular object actually goes out of scope. When an object actually goes out of scope. So what does it mean by what I mean by a scope? Suppose I sort of put a pair of braces in here around P1, for example. So P1 is what? P1 is just a person without name or any other information. But these two lines are now enclosed inside of this pair of curly brackets. And this pair of curly brackets actually defines a new scope. It's actually a new scope. So P1 will only live within this particular scope. As soon as it leaves this scope, it's gonna be destroyed. So let's see what's gonna happen. I'm gonna still leave P2 and P3 here, Kevin and the no name with the age of 20. But let's see what's gonna. Maybe I should give some name. I'm gonna call it Stewart. I'll give it a name. I'll give P1 a name. I'm gonna call it Stewart. And then it's gonna be more obvious. Let's just compile it, and then let's just run it. So this is when Bob was defined, and then this is when Stewart was defined. Bob was P, and then Stewart was P1, and now it's destroying Stewart. And then this is when Kevin was defined. That's P2. And then that's P3. The guy with no name but with the age of 20. And then destroying P3. And then destroying Kevin, P2. And then destroying Bob. So you can sort of see that the destructor is automatically called whenever an object goes out of scope. So P1 actually goes out of scope at the end of this closing curly brackets, because a pair of curly brackets actually define the scope, right? And the person P1 was defined inside this scope, so it's going to be destroyed at the end of this particular scope. And the same is true for P, P2, and P3. So P, P2, and P3 are all defined inside of this scope. The scope defined by this pair of curly brackets. So they are going to be destroyed when the function actually ends. When they actually goes out of this pair of curly brackets. So they are going to call the destructor for P, P2, and P3 before the end of this particular curly bracket. So basically that's a destructor. If you have to manage your memory by yourself, for example, if you are not using a standard template library container vector, you are defining your own memory block. How do you actually release the memory? How do you actually clean up the memory usage after the object is destroyed? That's going to be a lot more complicated, and those codes are also going to go into the destructor if you want to manage your memory by yourself, right? So we won't be able to talk about that kind of a situation in a lot of detail here, but maybe in future videos we can sort of cover that kind of situation. So in addition to the constructors and also the destructors, there's one more function that's kind of quite important. That's called copy constructor. The copy constructor exists because sometimes you would like to create a new object from an existing object, and this process is essentially like a copying. So you need a copy constructor. Here I did not actually define a copy constructor by myself, but the system, if you do not define a copy constructor, the C++ system is going to synthesize a default one for you. Suppose for example, if I define another P1, and then I'm going to initialize it using P. So this initialization is different from any of the initialization we have done so far. I'm actually creating a P1 object from an existing object that's P. And P has been initialized using this kind of information. Those are initialization information with the name, age, sex, and then the vital signs. And then I'm using P to initialize P1 actually. So I did not explicitly define a constructor of this kind of form that can take a person as its input, right? But the system is going to synthesize one for me. And the default behavior of this system synthesized copy constructor is that it's going to make an exact copy. It's basically a duplication of the same bit patterns used for representing P. So let's see what's going to happen. And we're going to sort of build it, and then let's just run it. So you're supposed to see two records of Bob. So here's the first Bob, and which was created here and printed here. And then you see a person P1, and P1 is also a Bob. It's exactly the same information. So that's sort of the default constructor. And then you can make modifications to P1 and change it to the information of another person, for example. And but you can actually change its default behavior. It's you can define your own copy constructor. Suppose I want my copy of the Bob to have a different name. For example, I want to have Bob underscore copy instead of have a name of Bob. So I can define that by I can sort of get that kind of behavior by defining my own copy constructor. And before we actually do that, we need to sort of pay attention to this particular. So here I have defined a person P1 and initialized using exactly the same information as P. So it's a copy constructor for P1. But here I have defined another P1 and then printed out a steward. And that printout is still here. It's still here. So you can sort of see the two objects with exactly the same name P1, but has different information in it. Right? The reason is that this P1, this steward, is actually enclosed in this particular scope. So within this particular scope, within this small scope, let's just call it scope. COP. Let's call it scope 1. Within this scope 1, the local variable or local object P1 is going to hide this global P1. So this P1 has the scope that's the global. So because it's defined inside of main, but this P1 has a scope of scope 1, this smaller scope. So inside of this scope 1, the existence of person P1 is going to completely hide the global P1. So suppose if I comment out this line, I do not define a new P1, and then I still do a P1.print, and you can see that this P1 is going to be Bob. Let's just build it and then run it. So that's the first Bob. That's the P.print, and then that's the P1.print, because P1 is a copy of P. So you still see a Bob, and now you see it's inside of the scope 1. Now P1 is again Bob. So if you do not introduce a new P1, do not introduce the same person, the same name again, P1, and then this P1 is going to be the same as the P1 that's in the global scope. So only when you actually introduce a new P1, exactly the same name as the global P1, then the global P1 is going to be hidden. You won't be able to access the global P1 inside of scope 1 anymore. So it will hide the global P1. So that's one of the things that we have to pay attention to about the scope. So, but now let's go back to copy constructor. How we can actually write our own copy constructor. So let me go back to the class definition here. So here let me write some comments here. Constructors. Sometimes it's just abbreviated as CTOR. Now let's write a copy constructor. So the copy constructor has to have a very special sort of format. It's still a constructor, of course, so it must still have the name person. So the function name is still present. But the stuff that's sort of passed as the input is going to be another person. So what you have to do is to person, so say P. But is that the correct syntax for a copy constructor? It's not. What you have to do is to pass a reference to a P actually. And then you have to sort of decorate this person reference with another modifier called const. We looked at this const behavior when we were sort of talking about when we're doing the string tokenization. When we actually try to call strtok, we have to cast away the constness of a particular character string. Here it's a const again. This const keyword actually means what? It means that this person P, or the reference of person P cannot be modified. When we talk about the reference, what I was telling you is that a reference is basically an alias to another object. And if you actually make modifications to the alias, the same modification is going to be reflected on the object that this alias is referencing to. So if you actually try to change the alias, it's going to change the original object. So here you're actually passing a reference to a person, and that's called P. And the P is actually referencing to a different person object. So if you actually inside of this copy constructor, this particular copy constructor function, if you make modifications to P, you're going to modify the original object that you're actually trying to copy. So you have to sort of make sure that you don't introduce that kind of behavior in this particular copy constructor function by enforcing it to a const reference. So by using the const keyword, you are telling the compiler this particular function is not going to make any changes to the input parameter P. And this input parameter P is going to be a reference to a person. The reason that you have to use a reference is because if you actually remove the reference, suppose you just do a const person P, it's logically it's not going to work because you are trying to define a copy constructor to define the behavior of copying. And here you're actually using the behavior of copying. You're basically passing a person itself into this copy constructor. So it's a circular logic. It's not going to work. So you have to sort of give it a reference to a person. So now let's try to define the function. So here again, I'm going to use my initialization list. I'm going to initialize my name with p.name. One thing that might confuse you is about this particular syntax p.name. Because now the name is a private data member. It's a private data member. So why can you actually make a copy? Why can you actually access? Why can you access a private data member by using a dot, right? Inside of a copy constructor, you can do that. You can actually do that because it's actually the same object. So you can actually see access. It's actually the same class. It's not the same object. It's the same class. So you can actually access the private data member. And then let's do age p.age, and then sex p.sex, and then what? Then vitals. It's gonna be p.vitals. And then we're still gonna leave the body of the function empty, so it's still a inline copy constructor. But what I was telling you is that I want to make modifications to the name. I don't want to just use the same name. I want to sort of append the name with the string copy underscore copy. So a string supports this kind of a plus operator, so you can just add underscore copy to the p.name, and then you can sort of modify the name. So it's not an exact duplication of the name, but you have modified the name a little bit. So let's just build it, and then let's run it and see what's gonna happen. So here it's Bob. Here it's Bob. That's coming from this particular these two lines. Here's the original Bob, and then that's the next that's the P1 person P1. I'm actually doing calling the copy constructor now, and this time it's actually calling my own copy constructor. So you have a name that's Bob underscore copy, and then the rest of the information are exactly the same. And then you have entered this scope 1, and then you are doing another person, so it's gonna hide. You're constructing another person that's called Stewart. Maybe Stewart, not Stewart. Stewart. So Stewart. So it's a different person. It's a different person. So you can sort of see it's a Stewart. So basically that's a copy constructor. Sometimes you may want to assign one existing object to the other existing object. So in this kind of case, you are doing an assignment. For example, if I have sort of initialized p1 to p, and I'm actually using the values inside of p to initialize p1. And suppose I would like to do an assignment. Here I have another p1 that's defined initialized using just a name. Suppose I would like to sort of do something like that. P1 equals to p. If I want to do this kind of assignment, how can I do that? Right? Can I do that? The assignment operation is so common in C++ codes. So the C++ language will automatically generate an assignment operator for you. So it is actually possible to do this kind of assignment using sort of a system-generated assignment operator. And you can see that the compilation, this piece of code actually passes the compiler. So it's not really a problem. But if you would like to define your own assignment operator, you can do that by yourself. You can just define your own assignment operator. So how do you actually do that? Right? This is also a demonstration about operators. How do you actually overload operators or operator overloading? Let's just call it copy assignment or operator overloading. You can overload an operator just like you overload a function. Operator in C++, an operator is basically just like a function. It functions just like a function. It has a similar kind of a syntax actually. So if I would like to define the operator equal to this assignment operator, all I have to do is to prefix the assignment operator with the keyword operator, and then I can use the whole thing just like a function name. So all I have to do is to define the body for this particular function actually, and this particular function can take an input, and in this case we'll just mimic the copy constructor here. We're gonna do const person reference p, and then what's gonna be the return type? The return type is gonna be another person, but it's gonna be a reference to a person actually. Because if you actually would like to sort of take the return value of the assignment operation and then put it into some other more complicated operations, you can do that. This syntax will allow you to apply further operations on the return type, and it will have effects. If you just remove the reference, it won't allow you to apply further operations onto the returned object. So that's gonna be sort of how we gonna sort of define our operator equal to the assignment operator. Now let's write the body of the function. The body of the function is actually quite simple. All we have to do is to sort of copy the name inside of copy all the private data members inside of P to the private data members of this particular class, and then age equals to p dot age, and then sex equals to p dot sex, and then what? Not set sex, and then vitals equals to p dot vitals. And then I have finished assigning all the private data members. So now what's going to be my return type? I'm going to return a thing that we have not discussed so far. It's called this. So when we are writing object-oriented codes, we need some way to access the object itself from inside of this object. And this is actually a pointer that's pointing to the current object. The object that's actually calling the operator equals to this particular function. And it's actually a pointer. So it's pointer to a person object. And this person object is actually calling this operator equal to function. So we have to remember two things. One is that this is used to reference the object itself from inside of this object. A second thing is that it is a pointer. And what we are expecting for the output is actually a reference to the person object. It's not a pointer. A reference is basically an alias to the object itself. So what we have to return is an object itself. So in this case, we have to sort of convert the pointer to the object itself. And the way for you to do that is to prefix the star in front of the pointer. And this is actually a universal thing inside of C and C++. So whenever you have a pointer, if you want to convert that pointer to the object that this pointer is pointing to, all you have to do is to put the star in front of that pointer, and then you get the object that this pointer is pointing to back. So this will actually return an object, and person reference is going to ensure that you are returning an alias or reference to the object. So whatever you are doing on the alias is going to be reflected on the object itself. And this code will compile, and it's going to pass the compiler. But this code still has some kind of a problem because it's actually quite a common mistake. Almost everyone makes this kind of mistake the first time you are writing this kind of operator equal to. You have to account for a situation that you're assigning the object back to yourself. So you have to sort of exclude this kind of situation. So you do this kind of assignment only when what? Only when this person P is not yourself, is not this. So to prevent this self-assignment, we'll need to sort of do some sort of comparison. How do we actually do the comparison? We'll compare something with this. We'll have to make sure that P, the stuff, the person P is not this. Is not this. But this is actually a pointer, right? It's a pointer. But P is a reference to a person. It's basically an alias of a person object. So you will need to sort of compare the address of P or a pointer to P with a pointer to this to the current object. So this is a pointer. So you have to convert P also to its pointer. So in C or C++, the language is like this. If you want to get a pointer or get the address of some object, you append this ampersand in front of the object. So you can think of this ampersand as the opposite of this star. So if you put the ampersand in front of object, you get the address of that. You get the address of that object. And then you can compare it with this, because this is also an address, it's a pointer. And if you put a star in front of pointer, then you get the object back. So you can think of the ampersand and the star as sort of the opposite operator. But the ampersand has to be applied onto a address, onto an object in order to get the address, and the star has to be applied on an address in order to get the object back. So that makes our code more complete now. So all I have to do is to make sure that this condition is satisfied. Basically, I'm not doing a self-assignment. I'm not assigning the P object back to itself. So if the address of P is not equal to the address of the current object, I do this kind of assignment. Otherwise, I don't do it and just return star this. So that's gonna give us the correct behavior for the assignment operator. So this is a copy assignment operator. But now let's give it a try. Let's try out this operator equals to and see how it's gonna behave. So here it's inside of the scope 1. I have some code here. So P1 was the inside of this scope. Let me see out scope 1. See out scope 1. So this is inside of scope 1. And I have defined an object P1 and initialized using just the name steward. And then I did a P1 print. So P1 is a complete object. It's an initialized object. It's an initialized person object. Now I am assigning P to P1. I'm assigning P to P1 actually. I'm assigning P to P1. Inside of this scope, there's no name that's called P. There's no person object that's called P. So this P is going to come from the global scope, which is a P that's sort of initialized here. So by doing this assignment, I'm actually copying the stuff that's inside of the global P to the content of this P1, local P1 that's inside of the scope 1. And then I can do a P1.print. And let's see what's going to happen. So P1 was initialized using the name steward. And then it was assigned the global P, global person object P. And then let's see what's going to happen. So where's scope 1? Okay, so scope 1 starts from here. And then ends here. So that's sort of the scope 1. Scope 1, the C out of the scope 1 actually. So at the beginning, P1 was initialized to steward. And then I did this assignment. Now P1 now has the name Bob and has exactly the same information as P. As P here. As P, that's Bob. So our assignment operator indeed works. So it actually works. So this is a assignment, right? But suppose we change P1, we change the initialization line for P1 also to an assignment, also using the assignment operator. Suppose I change it to like this, to like this. So here there's an assignment operator, and then there's another assignment operator here. Both of them are assignment operators, but the C++ is gonna actually have is gonna call different functions. What I'm gonna tell you might surprise you, because even though this looks like an assignment, but it's actually gonna call the copy constructor. This is also an assignment, and this one is gonna call the operator assignment. So they are actually gonna call different functions. So the first assignment operator is gonna call the copy constructor. The copy constructor is here, and the name is going to be appended with the string underscore copy. And then this is sort of the operator assignment function that we just defined. Copy assignment, it's a copy assignment. So you can sort of see the difference now. If I change this initialization from using the uniform initialization list to an assignment operator P, it's gonna call the copy constructor. It won't call the copy assignment operator. But this one is gonna call the copy assignment. So let's give it a try. So scope 1 starts here, and then ends here. And then here's the first the initialization. So I'm initializing P1 to P. So this one is actually going to call the copy constructor. So it's going to get a name that's Bob underscore copy. This underscore copy is something that's added in the copy constructor, but it's not existing in the copy assignment. And then that's the second assignment. But this time it's going to call the operator assignment. So this one actually has exactly the same name as Bob. It doesn't have the underscore copy. So it's actually two different calls.